I'm Chris Ostwood, CTO of Carnegie Robotics, and I'm going to be talking today about how we select 3D sensors in the systems that we build. First, just one slide on the company that I'm with. We're a 7-year-old spin-out from the National Robotics Engineering Center, which is part of CMU and the Robotics Institute there, but we're a for-profit company, and we build sensors as well as custom robotic systems. We have about 70 employees, half engineering and half sort of engineering support. That's our building, which is an old steel mill in Pittsburgh that's been converted into this new high-tech space that we operate in. So the talk today is going to start with some criterion definitions of how we think about sensors, and I'm going to go through that very, very briefly because of limited time. And the bulk of the presentation is on 3D sensor modalities, how they work, and how we have evaluated them both qualitatively and quantitatively, and hopefully this helps all of you select 3D sensors in future systems that you're building. So we separate performance criteria into performance criteria and non-performance criteria, and the weighting of all these different criteria changes dramatically based on the platform that your system is running, the kind of application that you're developing for, and the exact use of the 3D sensor that you're trying to select. So the field of view, or the density, or the data rate, or the depth accuracy, or the angular field of view, or the angular density, all of these things may have very different requirements for your application than other people's application. And the importance of each of these is also going to change dramatically by these sort of application-specific factors as well. And I put these up here not to go through each one of them point by point in terms of what is important where, but just to urge all of you to think very critically about which are the critical ones for the application and the platform and the use that you're building for. Just because someone else is using a particular kind of sensor on the same platform, if you have a different application, you may be better served with a different 3D sensor. And in terms of non-performance criteria, there's a whole host of other factors that we look at when we integrate sensors. Size, weight, power, cost. SWaP-C is a big part of mobile robots, especially things that are operating with their own power. But sealing, vibration resistance, the communication interface for the sensor that you're selecting, all these things can dramatically change the integration time and cost, and should be considered carefully while building your system. So going into some technologies, 3D lidars are fairly simple from an architecture perspective. They're very, very tricky when you get down to the physics of it, but you're basically sending out a pulse of light or a continuous wave of light, and then you're doing some measurement on both your emission and the return of that emission from the environment. Normally these are built with multiple arrays of single point sensors, and you actuate them in 1 or 2 degrees of freedom to build a 3D sensor from a 1D sensor or from a 2D sensor. And at some point, hopefully in the near future, solid-state LiDAR will be a more realizable and purchasable product. We're not quite there yet, but that will be an exciting time when that happens. The really nice thing about LiDAR is it has a constant error model. Even at very long distances, the 1 sigma accuracies are very good. They can be very long-range sensors, but you have real limitations in data rate and in horizontal and vertical density, and depending on the task of your system, that may prevent or limit the use of 3D LiDAR, which is where 3D time-of-flight cameras and stereo cameras can sometimes be more effective. So time-of-flight cameras are similar to 3D lasers from a emission and detection perspective. Excuse me. But instead of having a laser emitter, they have a modulated IR emission, and then you're actually doing that phase-based extraction on every single pixel in a photo array instead of on a single avalanche photodiode. This means that you get much better density, but because you're using a much smaller detector that's much lower power, and because you're emitting a broader field of view into the environment instead of a single point laser, the signal-to-noise extraction that a time-of-flight camera has to do is much trickier than a 3D laser. And this limits the range of these sensors as well as their accuracies. There's also some range ambiguity problems due to the modulated waves, and that means that you either have to operate these at lower data rates and have different frequencies that they operate at, or they actually have fixed distances that you just can't see or that mask and appear to be other distances. These are generally much denser than 3D lasers, but have higher power for the range that they're perceiving due to the higher density and the way that they're electrically built. They have generally intensity outputs. They almost act like a camera, and they bring their own illumination with their IR emissions, but they don't really have camera parameters that you can tune, and this is both an advantage and a disadvantage depending on the environment that you're in. Sometimes you run into problems where an object very close to the time-of-flight camera returns so much energy back to the detector array that it has a hard time doing that signal-to-noise extraction process on farther range materials in the scene. They're also susceptible to multi-echo returns, especially with things with specular highlights, and I have some examples of this on later slides. The last limitation, and this, again, this may or may not be a limitation depending on the exact application that you're building for, but they have limited horizontal field of view. It's very hard to both emit and detect this sort of information beyond 60 to 80 degrees, though that may change in the future. So stereo cameras work in a fundamentally different way. They work the way our eyes do by visually detecting texture in the environment and then comparing that texture between left and right camera, and the horizontal shift in texture position is inversely proportional to the distance that that texture is away. So when you close one eye and then you close the other eye, things that are close to your head move horizontally more than things that are very far away. Things at infinity don't move at all. And if you have a very accurate model of the distortion of your camera lens and a very good understanding of the particular arrangement of the two lenses, their distances and their mounting angles, you can relatively accurately construct the 3D scene that the cameras are looking at. One thing that is critical when you're looking at stereo cameras is their disparity search range. This is the number of pixels in the scene that the camera is actually searching before it decides there's no match and I'm going to give up. And the more pixels that you search across in a camera, the closer to the camera that you're actually able to observe 3D objects. So beyond or within that, things that are closer than that minimum range are generally invisible to the camera. The advantage of stereo is that you have very high resolution and density, but unlike these other forms of 3D sensors, their accuracy is limited at range. It's no longer a standard linear or constant error model. It's actually a quadratic error model. And as objects get farther away, the camera's ability to perceive them accurately decreases, just like my ability to perceive the distances to these chairs versus the back of the hall. Distance really affects the accuracy. These cameras are totally passive, which helps a lot in high obscurant environments. If you're operating outdoors with blowing dust or rain or snow or fog, if you visually can see through the environment to what the camera needs to see, so can the camera. It's not emitting anything into the world that it's trying to extract information from, so it's very robust to these sorts of obscurants. But it's a very computationally expensive process to do the stereo matching, this correspondence problem between the two cameras. So if you're doing stereo processing on a general purpose computer, you're limited in resolution or frame rate or the disparity search range. That's part of why we embedded the stereo matching process inside of an FPGA in our cameras. The top two cameras here. That reduces the power required to do the stereo matching process, as well as reduce the latency to get the 3D data. I talked earlier about the nonlinear error model here. This gives you some sense of what I'm talking about. The purple line on the bottom is LiDAR, and then all the other curves here are different stereo cameras with different baselines and different horizontal fields of view. And you can see that, depending on the range, you could have better or worse accuracy. And this isn't a game, this isn't a showstopper for lots of applications, but the software that you're building really needs to understand this error model to accurately use and reasonably use stereo data. I'm just going to skip over that for time. So I have here a couple slides on a qualitative comparison between we did between these sensors. All these scenes are similar, where we have a cart with a chessboard on it. A person walks into the scene, bends down, picks up a chess piece, moves it to another spot, and then walks out of the scene. This is a rotating 3D laser, first with 8 seconds of persisted data, and then we speed up the rotation rate and just show 1 second of persisted data. And you see intuitively the wide horizontal and vertical field of view of this rotating planar laser. But because of the density and the persistence, it's actually very difficult to make out the person. And you have very different density in plane or in scan, as well as scan to scan. With the higher data rate, you get more accurate information about the world temporally, but it becomes harder and harder to pick out different features in the scene because of the density reductions. So trying to run an object classifier on this sort of data is possible, but you're you're adding a lot of difficulty to your process. And you'll also see that between the cart and the ground, there's actually returns that are in the middle of the air. These are mixed pixel returns where the laser beam hits partly on the cart, partly on the floor, and you get a return in mid-space. That's not actually a real return. It's balanced between those two different objects. This is the same scene from a low-cost time-of-flight camera, sort of consumer grade, and you see the much lower resolution, much lower field of view, much lower data rate in comparison to the LiDAR that we were just looking at. You see some returns in the middle of the air that are just completely false and not actual returns. And you also see that about half the floor is missing, and I can't really explain this. This is shiny concrete floor, a couple of meters away. It doesn't really make any sense why half the floor is missing. You see that the back of the cart is very bowed, and here we have flipped to a intensity view of the same data instead of an axis coloring, and you see the sort of flashlight effect you get when you're viewing this data because of the IR emitted data, or the IR light that the camera is basing all of its range returns off of. This is an industrial camera, and when someone walks in front of it, it completely distorts the scene. If you didn't know that was going to happen, that could really mess up the map that you're building of this environment. And a similar thing happens to the background when the person's walking in front of it. It'll flip to a top-down view in a second, and you actually see that it sort of ripples and rolls and waves the background. Again, this is maybe due to multipath returns, but it's not really explainable. You also see a bunch of data in between the person and the back wall that they're standing in front of, sort of the same sort of mixed pixel return problem that LiDAR cameras have, or that 3D LiDARs have. And you also see some pretty severe bowing to the concrete floor caused by multipath. This is the same data from a stereo camera. This is from the Multisense, the camera that we build. And you see that there's a lot higher density here, but you now start to have that range accuracy problem. The data close to the camera is much more accurate than the data at that back wall, which is 3 or 4 meters away. There's a lot more range variance on that stack of panels behind. Our cameras can be built with color imagers, so you have one-to-one perfectly correlated color with range, which is useful in some applications. But you also see a hole in this data in the floor and a bunch of returns below the floor surface. This is actually an invalid return. The camera is seeing a reflection of a light on the concrete floor, and it can't differentiate that reflection from reality, so it's actually giving us returns as though that light were reflected underneath the floor surface like a mirror. One nice feature about our cameras is that you can dynamically adjust the stereo post threshold and change between very dense and less accurate data, or you can tell the camera, actually, I just want the really confident data and I want less of it, and you can dynamically change those sorts of variables as the camera's operating. And you see here just the density and the accuracy at close range of this data. It's very useful in these sorts of ranges. One other interesting thing about stereo is that it doesn't have to be totally passive. You can build active stereo systems, and here this is the same camera, and we're turning on and off an IR pattern projector. The stereo algorithm has no knowledge of this pattern. It can be totally random and arbitrary, but it's just providing additional visual texture to the world, which allows the stereo algorithm to be more accurate and to get better information in low texture and lower texture parts of the scene. This is really important for stereo operations indoors. Things like drywall and indoor paint are very smooth, and without any visual texture, stereo algorithms fall over and can't give you any data. You can also build stereo cameras from thermal imagers. You don't need to use the visible spectrum. This is a bimodal optical and thermal stereo camera we built. The top set of images here is data from the visual pair. The bottom set of images is data from the thermal pair. And you see that the ground doesn't have enough thermal texture to give us range returns, but the people in the cars do. And there's actually enough temperature change in the air around the power lines that we're getting range returns off of those. That big diagonal stripe across the sky is actually the power lines. Okay, so going into some quantitative testing. This is a material test board that we built up, and we've done a bunch of different testing on different sensors, and I just wanted to highlight a few things There's a lot of information on these slides and not enough time to go through all of it, but I just wanted to show the effect of a couple of different changes to the environment. This is with sort of normal fluorescent lighting and then high intensity halogen lighting. The laser from this vendor saw a shift of 2.5 centimeters on the white areas. Similar kind of laser from a different vendor had 50% more noise in the low lighting environment, but then when you turn on the high halogen or the high IR from the halogen lights, the range accuracy drops dramatically for this sensor. Similar kind of 3D perception technology. Different vendors have different implementations and have these sorts of regressions potentially. This is a time-of-flight camera, and you see that there's higher range noise on dark objects, and that turning on that halogen light with high IR increases the range noise by a factor of 2 to 5, depending on the material. A stereo camera doesn't have those sorts of intensity-based accuracy reductions, but it does have accuracy reductions as you pull the camera away. So this is a visualization of range accuracy and variance at close range and at long range for that 7-centimeter camera. Sensors can also change over time. This is 2 different units. We put them on a flat wall and did scans of this flat wall and slowly pulled the sensor away. So each line of data here horizontally is pulling that 3D laser 5 centimeters away from the wall. And you see that this one unit, Unit A, actually changed in accuracy from the first time we tested it in January to when we tested it again in July. And the distortion that it was seeing on that wall was actually emission angle and range dependent. It wasn't just that there was a bad distance or there was a bad clocking angle, but the combination of those two factors had like bad lobes of data within this field of view, which was very surprising and not expected. And then the exact same model, but a different actual physical unit from that same vendor didn't have those sorts of problems. We've also done, we're sort of still in the process with this, but we've been trying to develop better tools that let us understand 3D resolution accuracy, both in depth and well as horizontally and vertically. So we've built a 3D target modeled after the US Air Force 1951 visual target that's used for MTF and 2D camera testing. And we've recreated that target in 3D space with vertical and horizontal bars of different sizes and at different distance standoffs from the backboard. And this is what this target looks like through an industrial time-of-flight camera. You see horizontal and vertical bars. The left image is an error image. White is the model and the measure lining up. Red is the model is in front of the measure, and blue is the model is behind the measure. And then on the left side is just a raw range image showing a 2.5D height map. One thing that's really interesting in this is we added this slanted target you see below the bullseye, this sort of a 3x6-inch wedge on the target, and that totally disappears. You really can't see it in the range image. The top half is visible, and then the bottom half of that ramp is completely gone, and you see that reflected in the big red stripe in the model versus measure error image. We believe this is happening because that slant is actually reflecting IR energy away from the camera back down to the floor, so we're not getting a good return off that wedge, but we get a much better return off the things that are parallel to the camera. You also see that there's sort of equal performance of this camera both horizontally and vertically, but it's relatively low resolution. Even these large targets only have about 3 pixels of data on them, and then you can see the whole top left corner, the very small features, completely blend into the background. They don't have enough size horizontally or vertically to be visible, and the depth accuracy of the camera can't pick them out either. In comparison, stereo is much higher resolution, so we're able to see the smaller targets, but because of the stereo matching process, we see very different performance in horizontal and vertical bars. The horizontal bars at the bottom left, you actually see the blue background between them. They're isolated and individual. And then the vertical bars actually web together because of the horizontal stereo matching process. You're searching left to right, and the accuracy of the camera in that direction is worse vertically. So you end up blending features, sort of smearing them horizontally, and that blends those vertical bars together. That actually is advantageous when you're trying to see the small vertical bars, which are directly above that large one. You know, the top left features here, even the very smallest vertical bars are visible to the stereo camera because of this blending effect. There is no perfect sensor. They all have limitations. They all have edge cases. And you really need to think carefully about your environment, the application, the platform, and balance all these requirements and balance the sensor performance appropriately. It's really important to collect data from your environment, really important to test things thoroughly, to look at data sets that are available. If data sets aren't available, please ask your sensor manufacturer, like us or like other folks, to provide that to you. That really helps you understand the performance in the environment. And I welcome people to publish more data sets. It's very useful to sort of share these sorts of things with the community and to learn from each other's experience in testing and integrating these systems. We have all these videos replicated on our website, and then there's more information about our products on our website as well. And I'll also say we're about to launch some new versions of our products. There's a sign up for our newsletter link on that page, and when these new product announcements are available, I'd be happy to share that with you guys. Thanks so much for your time, and I have a few seconds for questions.
Just got time for one quick question. I think you've made it to the mic first. Sorry about that, but we'll have time in the evening if you contact Chris.
Hey, sir. This is working. Oh, okay. Hey, sir. I'm Brandon Shrewsbury. We've been emailing quite a bit. I've been wondering in the Multisense SL, when you do a calibration check, it checks the stereo to the LiDAR. Mm-hmm. And I've always wondered, do you use ground truth when you're setting up your calibrations in-house? Because you've noticed that the LiDAR obviously has different error depending on the texture, and I had noticed that the stereo had the same thing with our material.
Yeah, the stereo accuracy can change based on the material and the texture. When we do the stereo to LiDAR calibration, we actually synthetically generate sort of a fake disparity image from the LiDAR data, and we do all of our estimation in disparity space, which balances out the different error models between the two different sensors, which is also really important. If you try to align stereo and LiDAR in XYZ space, you have a much greater difficulty because of the error model of stereo data. And in terms of the materials that you should use, you need something that has visual texture for the stereo to work off of, and you want something that doesn't cause distortion to the laser data. So checkerboards are great for calibrating camera data, but in most laser data that we've looked at, you actually see the checkerboard in the laser data. The white and the black appear to be different distances away. So when you're doing these laser to stereo calibrations, it's important to pick materials that don't have as much visual contrast between them, and then you aren't introducing that sort of range error in your LiDAR data.